Hi, it's Mr. Duffy. Welcome to chemistry. Today our topic is density. Let's go ahead and get started. Density is probably a topic that you've covered in other science classes, but we need to cover it in chemistry because chemistry is the study of matter. And so we want to talk about this important topic to start off our year. So let's talk about what density is. Density is a comparison between the amount of matter in a particular amount of space. Amount of matter we normally measure is a term for its mass, how much something weighs, and a certain amount of space that would be considered its volume. Okay, so we're going to take a look at a couple pictures and just kind of try and analyze and get a feel for what density is. Here I have two different pictures, and I want to imagine them in two different scenarios. Imagine yourself standing at the top of a skyscraper and looking down, and these are people's heads in a particular city square block, maybe on the sidewalk. From there, which one is more dense? Well, hopefully you pick the one on the right because there are definitely a lot more heads on the square on the right than there are on the left. There's a lot more matter in the same amount of volume. Okay. Now I want to flip this scenario around and say, well, now this is not heads on a city square. This is holes in a block of Swiss cheese. Now that changes the scenario. It changes what's going on. And I think you would hopefully realize that if it's in that scenario, the one on the left is more dense because it has less holes. And so there is more matter in the same amount of space. Okay. Density really depends on what the object is. Now let's take a look at another scenario. Now, instead of changing the number of holes, what I've done is I've changed the volume or like the amount of space there is. Both of these objects have 5 holes or 5 people in them, and so now it changes our answers again. Imagine this is from the top of the city skyscraper again. Which one is more dense? Well, since there are 5 people in both scenarios, and the one with smaller volume is more compact, then the one on the left is more dense. If we switch to cheese, thinking about it as Swiss cheese again, well, they both have 5 holes in them. So the one that would be more dense would be the one on the right, because again, there's more matter. It does occupy also more space, but again, since they have the same size holes, definitely the one on the right is more dense. Now, let's get to a more uh, mathematical way of representing density. And density is the amount of matter in a particular amount of space. We say that's mass and volume, but it's mass per space. So mass per volume means we divide. So the amount of mass divided by the volume equals our density, which we represent with a capital D normally. Units for mass can vary, but for the most part, we're going to be using grams as our unit for mass. Volume, also, the units can vary depending on how you measure. Normally, we measure solids with a ruler, and so we would use centimeters, centimeters times centimeters times centimeters, or centimeters cubed. And if it's a liquid, we normally would use a graduated cylinder, which we often represent as milliliters as being our volume. And these are not the only units for mass and volume, but very commonly you're going to see density is expressed as grams per centimeter cubed or grams per milliliter. That is not, again, the only ones you will see for density, but it is definitely the most common. Now, since density has 3 different variables set up, we can actually set this into what's called like a unit triangle. Um, it becomes useful for equations that have 3 variables, but it does not have to be used. So if we set our variables up in this triangle, what it allows us to do is put 2 pieces of information in to solve for the third. It allows us to get the equations fairly easily of which one would be which. Let me just give you an example. Let's say I am trying to solve for the mass of an object. If I remove the mass from my triangle, what ends up happening is density and volume are right next to each other. So that would mean I would multiply by density times the volume to get the mass. Now, if I'm trying to do this again, and let's say I'm trying to find the volume, I can do a very similar situation, but I remove the volume. Now, mass is on top of density, so what that would mean to calculate, I would do mass divided by the density would give me the volume. And then our traditional sense for the traditional equation is mass over volume to find our density. So again, you can see how the triangle is useful for finding the three different variables. Another way that is useful to find density is actually to graph it. Graphs, we know in science, are very good at analyzing lots of data all at once, and density is no different. So density can be expressed if we make a graph of the mass of an object over in its volume, the volume of the objects. We can put multiple objects on the same graph and again, then compare. So I have water on this graph, and then I have objects E, F, G, and H. We don't even care what those objects actually are, but what we can do is, again, look at them and then again compare how their mass and their volume relate to each other. One thing I'd like to note, especially, is that all of these start at 0. And I think that really should make sense because if you have 0 mass, it's going to occupy 0 volume. That, again, is if basically you have nothing, so it should not weigh anything. They all start at the same point. But from there, you can see that those 5 lines have different slopes. And I'd like you to think about what does the slope represent in a graph of mass and volume. So our rise over our run is how we find slope. A rise is the change in vertical components over the change in horizontal components. And my vertical component in this case, the y-axis, is mass. So it's our change in mass over our change in volume. And change in mass over change in volume is the exact equation for density. So what the slope represents when we have a graph of mass and volume is it represents our density. And so I can see just by looking at it which one has the highest slope. Well, letter E does. Letter E is the highest slope, so that must mean it has the highest density. Letter H has the lowest slope, so it must mean it has the lowest density. And I also can compare it to water. So water is, again, one of an important density. Again, it's also kind of nice. Density of water is 1, so it has a slope of 1 as well. And anyways, what I can tell from looking at that is I can tell which objects are going to sink and which objects are going to float from this graph. Anything that has density lower than water will float in water. So letters G and H will float. These two will float, whereas letters E and F will sink because their density is higher. They're higher on the graph, but again, they're going to sink in the water because they have higher densities. So again, lots of stuff going on here, but again, hopefully you see that densities can be are very easy to interpret using a graph. Let's take a look at some problems. So what I have here is a setup of kind of like a experiment we might do in class for finding the density of an object. To find the density of an object in class, we would need to get its mass and its volume measurements. What we're trying to find here is the density of some miscellaneous little chips of material. Don't know exactly what they are, but maybe by finding the density, it would help us identify what those chips are. So what we're going to do is we're going to get its mass and then use the water displacement method to find its volume. And what I have is close-up pictures of the mass measurements and the volume measurements. And so we'll have to, again, practice using our measurement skills to be able to do this. As far as the scale goes, we just have to read the scale. What they did not do is they did not press the tare button on the scale to actually set up and find the mass. So we're going to have to subtract out the mass of that container. What we have with the chips in it is 62.81 grams. The empty container by itself is 4.52 grams. If I subtract those two from each other, I get a mass of 58.29 grams. That would be the mass of just the chips themselves, not the container. So now we have the mass. Now we need to find the volume of those chips. And so what we have is, again, the water displacement method. If the object had a regular shape, we could actually calculate it just using a ruler, length times width times height, possibly. But these are weirdly shaped, so we're going to use the water displacement method to figure it out. What I need to know is where did the water start and where did it end? And based on that, then I can subtract them. So in the first graduated cylinder which just has water in it, we have 50, 51, 52, 53. I would, again, say 53, and we're allowed to estimate that last place, so I'm going to say 53.8 milliliters. Again, you might say something slightly different, but I think it's somewhere around there. And after the solid is put into the graduated cylinder, we have 85, 86, 87, 87, and then I'm going to say zero point 0.4 milliliters. Again, I'm estimating that last place, but again, you're allowed to do that. What we need to do now is find the difference in volume, the change in volume based on the water displacement method. And subtracting those, it gives us a volume of 33.6 milliliters. Now we can find the density by doing mass divided by volume. The mass given to me, or that I solved for earlier, was 58.29. And I'm going to divide that by the volume that I just found using the water displacement method, 33.6 milliliters. So dividing those two gives me a density of 1.7. Now, I could use that density to maybe figure out what this object is probably made of. Now, I'm not going to get an exact answer. I'm just going to make a guess. But metals normally have a little bit higher densities, sometimes around 2 or 3. Again, it depends what the metal is. Um, so I'd probably guess that this was probably maybe some type of stone or something like along those lines. Um, I might have to do some other testing to figure that out, but not likely a plastic. Plastics normally have densities a little lower or closer to 1. So, anyways, probably some type of stone would be my guess. Maybe a very low density metal is another possibility. Okay, so anyways, finding the density would allow me to possibly figure out what the object is made of. Now, my last slide, but one of the things that is also unique with densities is how liquids interact with each other. When you have liquids that do not mix together, we call those immiscible liquids. Um, Example would be oil and water. When they mix together, they don't combine together. They don't form a homogeneous mixture. They form a heterogeneous mixture where they separate apart. And they separate based on their densities. Now, higher densities sink. They're more dense, so they go to the bottom, and lower densities are on the top. That's kind of the answer to the first two questions. Which layer has the highest density? The green layer obviously then has the highest density because it is on the bottom. Which one has the lowest density? I don't have a yellow marker, so I'm going to do it in red. The yellow one is on top, so it must have the lowest densities. I'm given a table of densities, and I could match them up to which one the layer likely is. So again, something that has the highest density would probably be green, 10 centimeters, 10 grams per centimeter cubed. And then red would probably be the next one, followed by blue, which I do have a blue, and the last one, yellow, which I don't have, would be 3. So again, hopefully this video has helped you understand better the concept of density. Thank you for watching.